Well, welcome to Hoverbot TV, and tonight we're going to be reading about a Canadian-designed wooden quadcopter powered by a human. And I'm not sure if we'll be able to see these pictures, but there you go. There's them assembling it. And one of the rotors here. And I'm not sure if you can see that, but there is the pilot. So we will go into the article, and it's for the Sikorsky contest, which is $250,000 for the human-powered helicopter, I think, or helicopter-based flying vehicle. I'm not too sure. You'd have to look it up, but it is the Sikorsky Inventors competition. And haven't practiced reading through this, but we will find out if I stumble too many times to do it in one take. And here we are. There's Liftoff, the title of the page here. Canadian Innovator is a trade publication. And here you can see the 4 rotors position. Now it's all trussed work, spars and that kind of thing, and personally I'd be quite amazed if they can do this. Canadian inventors have come up with a lot of great inventions over the years, and you know, things like LiDAR and that kind of stuff that gets adapted to other people's systems later. But basically this carbon fiber and wood, balsa wood actually, quadcopter is their bicycle-powered flying vehicle, and it spans, it looks like it's at least 30 meters across or something, I'm not sure, but let's read about it. A Canadian human-powered helicopter moves ever upward in the quest to take home the coveted Sikorsky Prize. Taking flight, using only human muscle power, took an exciting step forward this summer, with several strong attempts to win the Igor I. Sikorsky human-powered helicopter competition. Unclaimed since its inception in 1980, the Sikorsky Prize requires a human to hover 3 meters off the ground for at least a minute within a 10 square meter area. It's also the 3rd largest monetary prize, $250,000, in aviation history. To date, there have been over 30 serious attempts to win it, but only 3 teams have achieved brief periods of flight so far. The Canadian contender is called the Atlas, which features 4 independent rotors connected by a large truss structure. At its center, Dr. Todd Reichert, Atlas project manager, pilot, and national-level speed skater, provides the power atop a specifically designed bike frame designed by Toronto's Cervelo. Like the bike, carbon fiber is a key component used in the drivetrain of the truss, and the main spars the rotor. The rotor ribs of the Atlas are polystyrene balsa wood with mylar skin. The controls are on the handlebars of the bike, with collective and pitch actuated through the end shifters at the vehicle's roll adjusted with the brake levers. The team behind the Atlas is known as Lovell, a group of students and professionals supported by donations and individuals, research grants, and corporate sponsors. Core members such as aerospace engineer Cameron Robertson has been working together since 2006 on the world record-setting Snowbird human-powered Ornithopter, a flapping wing aircraft, as well as several high-speed bicycle designs. Fellow team members Dr. James Delorier is the man who spearheaded the successful Canadian motorized Ornithopter flights a few years ago. The Atlas uses 4 rotors, a design that requires low amount of muscle power, strong stability, and greater ease of construction comparison to other models. Now, anybody who's flown quads or hexacopters or octocopters and built them and dealt with the motors and, you know, the efficiency of each motor affecting the other motor and that kind of thing, this is quite a huge chunk to bite off to actually build a 4-rotor. Can't say anything but spindly helicopter. Personally, I think that there's probably going to be a winner, but it's not going to be with a four-rotor helicopter like this. Perhaps with a multi-rotor 1632 rotor system with rotors that are actually structurally robust and versatile in wind and outside and that kind of thing, then possibly. But anyways, let's get back to it. Optimal structure design specifics were hammered out by Robertson using carbon infinite element analysis (FEM) code with 12 degrees of freedom, written by undergraduate engineering team member Trevor Evans. This program determined the forces on every part of the structure under a given loading condition. Then, with internal forces that are calculated from the displacements given by the FEM, you conduct a failure analysis, Robertson says. That includes failure of wires, buckling, and several modes of failure, of material failure, of each layer of carbon in every tube. Almost lost the camera there. We're filming with the hoverbot, so bear with us here. Oh, no, it's balancing on a concrete core here. I'm having trouble. Okay, there we go. Stay. The Atlas also needed a truss structure which would reduce the overall weight through allowing the material failure of structure to be closer to the buckling failure of the long supported beams. Carbon fiber tubes are very thin and most of our tube designs are large diameter, therefore prone to buckling, explains Robertson. Using smaller tubes was the answer to prevent the walls from buckling before the carbon fiber fails in comparison. So the surface area and the buckling of the surface area, the greater the surface area, the greater the chance of a buckling point to start. So let's read this on here. Given a set of roughly 30 design variables, including rotor geometry, lift, coefficient, spar diameter, and tube thickness, the program then computed the total mass of the proposed aircraft design, the required flight power, and the stresses in all the various components. Reichert then employed a computational optimizer to determine the design that would minimize the required power, the lightest possible structure which passed all the failure tests. The optimizer turned out to have a lot of trouble analyzing the discontinuities, the non-realistic design solutions that popped up, and Reichert eventually used a gradient-based optimizer. It provided the robustness and the speed to get the job done, converging every time and working about 100 times faster, he said. The downside was that I had to optimize the discontinuous variables by hand. After many design tweaks and after 240 optimizations, a solution was arrived upon, a final structure with the weight below the team's estimated start of the project. Now, what works in the computer and what works in real life, completely different factors. And you can see how the computers showed them how to build this, but it's turned out into this very, very fragile, spindly four-rotor concept, which it just doesn't look like it could actually handle the torque of the pedaling even, or the drivetrains or anything like that. I've worked with a lot of belt drive systems on big motorcycles, and chain drive systems and direct drive systems and shaft drive systems like on BMW. And the torque involved for like massive horsepower is quite insane actually when you consider the size of a shaft on a BMW and the horsepower. And this could be maybe 2 horsepower, this flying vehicle, or 4 or 6 or whatever. But I just don't see that the transmission of power over the great distances would be able to be efficient. So you're going to lose a lot in twisting and that kind of thing. So anyways, let's go to the controls. The controls for the Atlas are fundamentally different than the controls of a regular helicopter. In our design, there are canards at the tips of the rotors that use aeroelastic twist of the rotor to increase and decrease lift on the entire blade. More at the tip than at the root, Robertson notes. So the challenge was to find a method of actuating the rotors that didn't require too much additional force from the pilot, or too much weight in the mechanism. It was all novel and never seen before for a helicopter like this. Robertson says that the next great difficulty was balancing the required control authority with the structural flexing. When you change the control surface orientation to change the lift of the rotor, the entire rotor flexes up and down with the change in lift. He noted sometimes that this flexing is substantial, meaning that the tips of the rotors collide with the ground or bracing wires throughout the structure, which is also a serious risk. Another thorny challenge was deciding on how large to make the entire helicopter. Bigger is better, but of course the larger the structure, the more inconvenient and difficult to deal with, says Robertson. The rotor spool was also a big challenge. It is very large and lightweight structure that involved many iterations. One thing that wasn't a problem was creating the well-prepared and experienced team. Members were recruited from the University of Toronto's Human-Powered Vehicles team, says Robertson. These students were familiar with the composite materials and advanced computational design techniques, which they use each year to make streamlined bikes capable of 120 kilometers per hour speeds. We expected to get an Atlas team together to be more of a challenge, but everybody we approached was extremely enthusiastic and everyone did unbelievably well. During the summer's testing round, Atlas achieved flights of 15 seconds at a height of about 0.5 meters. Let's read that again, folks, because we don't know if this is actually manned or unmanned, but if this quadrotor lifted off for 15 seconds, then obviously it's not too spindly, but I've yet to see a video of this thing flying, so let's hold our breath on that one a little bit longer. During the summer's testing round, Atlas achieved flights of 15 seconds and at a height of about 0.5 meters. That's a foot and a half or so, 2 feet maybe. We need to develop more familiarity with the controls and how the helicopter handles. And we also need to do additional trimming and tuning of the structure, Robertson said. We also need to find a new test location that is less damaging to the helicopter during a crash landings that's also available on weekends. Now that the student part of the team is back in school. So they're back in school, so they're looking for like a big, I guess, stadium or something like that probably. Robertson says there were a few reasons why the Sikorsky Prize attracted the attention of Aero Velo. The difficulty of the design problem itself was a pull, and the multidisciplinary approach is an excellent opportunity to work with and mentor other engineers, he explains. Working on the entire system is a complex and large task, yet simple enough that everybody can have an excellent grasp of the designs of the whole. It's lots of fun. So there you go. I'll try to show you the pictures once again. Sorry about my reading. Pretty tiring day today, but there you go. Whoa. Using the hoverbot again here, folks. Okay. I'll try to get a good picture of this. I hope you can freeze that or something, but the hoverbot shadow is getting in the way. There you go. So that's them in the field there, assembling the human-powered quadcopter. So, get inventing, guys. $250,000. Probably costs you a lot more to build your flying vehicle, but it is $250,000, so also it's not that expensive. Anyways, that's the Canadian human-powered wooden quadcopter. A reality, not a myth.